One stage op-amps. All of the differential amplifiers studied in chapters 4 and 5 can be considered as op-amps. Figure shows two such topologies with single-ended and differential outputs. The small signal low frequency gain of both circuits is equal to GMN R0 N parallel R0 P, where the subscripts N and P denote NMOS and PMOS respectively. This value hardly exceeds 20 in submicron devices with typical current levels. The bandwidth is usually determined by the load capacitance CL. Note that the circuit of figure A exhibits a mirror pole. Here you can see in this figure simple op-amp topologies. Whereas that of figure B does not. A critical difference in terms of the stability of feedback systems using these topologies. The circuits of figure suffer from noise distributions of M1 minus M4 as calculated in chapter. Interestingly, in all op-amp topologies, at least 4 devices contribute to the input noise: 2 input transistors and 2 load transistors. In order to achieve a high gain, differential cascode topologies of chapters can be used, shown in figures A and B, for single-ended and differential output generation respectively. Such circuits display a high gain on the order of GMN R0 R square and R0 square and GMP R0 R square not P, but at all cost of output swing and differential poles. These configurations are also called telescopic cascode op-amps to distinguish them from another cascode op-amp described below. The circuit providing a single-ended output suffers from mirror pole at node X, creating stability issues. Figure cascode op-amps. As calculated in chapter, the output swings of telescopic op-amps are relatively limited. In fully differential version of figure B, for example, the output swing is given by 2 VDD minus VOD1 plus VOD3 plus CSS plus mod COD5 plus mod COD7, where CODJ denotes the overdrive voltage of NJ. Another drawback of telescopic cascodes is difficulty in sorting their inputs and outputs. Example, to implement a unity gain buffer similar to circuit of figure. To understand the issue, let us consider unity gain feedback topology shown in figure. Under what conditions of both M2 and M4 in saturation, we must have Vout less than or equal to Vx plus Vth2 and figure cascode op-amp with input and output shorted. V out greater than equal to VB minus VTH4, since Vx equal to VB minus VGS4, VB minus VTH less than or equal to V out less than or equal to VB minus VGS4 plus VTH2 depicted in figure. This voltage range is simply equal to Vmax minus Vmin equal to VTH4 minus VGS4 minus VTH2 maximized by minimizing the overdrive of FUM but always less than VTH2. While a cascade op-amp is rarely used as a unity gain buffer, some other topologies such as switched capacitor circuits of chapter require that the input and output of op-amp be shortened for or part of the operation period. At this point, the reader may wonder how exactly design an op-amp with so many devices and perform parameters. It may be clear where the starting point and is how the numbers are chosen. Indeed, the actual design methodology of the op-amp is somewhat depends on specification of the circuit that the circuit must meet. For example, high gain op-amp may be designed quite differently from a low noise op-amp. Nevertheless, in most cases, some aspects of the performance, example output voltage, swings and open loop gain are of primary concern. Pointing to specific design processes, the following example illustrates these ideas. In order to alleviate the drawbacks of telescopic cascade op-amps, namely limited output swings and difficulty in shorting the input-output, a folding cascade op-amp can be used as described in chapter 3, illustrated in figure. And in an NMOS PMOS cascade amplifier, the input device is replaced by the opposite type while still converting the figure folded cascade circuits input voltage to a current in the four circuits shown in figure. Small signal current generated by M1 flows through M2 and subsequently the load, producing an output voltage approximately equal to GM1 R out V in. The primary advantage of the folded structure lies in the choice of the voltage levels, because it does not stack the cascade transistor on the top of the input device. We will return to this point later. The folding idea depicted in figure can easily be applied to differential pairs and hence operational amplifiers as well shown in figure. The resulting circuit replaces the two circuits one in figure A. One bias current ISS provides the drain current of both the input transistors and cascade devices, whereas the figure B, the input pair requires an additional bias current. In other words, ISS1 is equal to ISS/2 plus I3. Thus, the folded cascade configuration generally consumes higher power. 2 in figure A, the input CM level cannot exceed VB1 minus VGS3 plus VTH1, whereas in figure B it can be less than VB1 equal to VGS3 plus mod VEHP. It is therefore possible to design the latter to allow the shorting on its input and the input terminals with the negligible swing limitation. In the contrast to the behavior. This is in contrast to the behavior. Figure folded cascode op-amp topology depicted in figure B. It is possible to tie the envelope of M1 and M2 to their common source point. We will return this idea in chapters. Let us now consider maximum output voltage swing of the folded cascode op-amp shown in figure, whereas M5 minus M4 replace the ideal current sources of figure B with proper choice of VB1 and VB2. The lower end of the swing is given by VOD3 plus VOD5 and the upper end of VDD minus V mod VOD7 plus mod VOD9. Thus peak to peak swing on each side is equal to VDD minus VOD3 plus VOD5 plus mod VOD plus mod VOD9. And the peak telescopic cascode of figure A. On the other hand, the swing is less by the overdrive of the tail current source. We should nonetheless know that the carrying a large current M5 and M6 in figure may require a high overdrive voltage in their capacitance contributions to node X and Y2 is to be limited. Figure folded cascode op-amp with cascode PMOS loads. Now we now determine the small signal voltage gain of the folded cascode op-amp figure using the half circuit depicted in figure A and writing mod AV equal GM R out. We must calculate GM and R out as shown in figure B, and the output short circuit current is approximately equal to the drain current of M1 because of the impedance in looking into the source M3, that is M3 plus GMB3 minus 1 parallel to R03 is typically much lower than R01 parallel to R05. Thus, GM is similar to GM1. To calculate R0 to use figure C. R03 similar to GM7 plus GMB7. R09 to write R0 similar to R2P to GM3 plus CMB3 R0 follows that mod AB is similar to GM1 GM3 plus GM3 R03 R1 parallel R05 parallel to GM7 GMB R07 R9. How does this value compare to gain of telescope op-amp for comparable device dimensions and bias currents? The op-amp, the PMOS input differential pair has bits lower transconductance than NMOS pair. Furthermore, R01 and R05 appear in parallel. Here you can see in these figures A half circuit of folded cascode op-amp, B equivalent circuit with output shorted to ground, C equivalent circuit with output open. Reducing the output impedance, especially because of M5 carries currents of both the input device carries the current of both the input device and the cascode branch. As a consequence, the gain in equation is usually 2 or 3 times lower than that of comparable telescopic cascode. It is also worth noting that the pole at the folding point, that is the sources of M3 and M4, is quite closer to the origin and associated with the source of cascode devices in a telescopic topology. In figure A, T dot arises from TGS3, TSB3 and TB1 and TGD1. Figure effect of device capacitance on the non-dominant pole in telescope and folded cascode op-amps. By contrast in figure, T dot contains additional contribution due to GD5 and GD and CGD5 and CDB5, typically significant components of because amplifier by wide enough to carry large current with by a small overdrive. A folded cascode op-amp may incorporate NMOS input device and PMOS cascode transistor illustrated in figure such could potentially provide higher gain than the op-amp of figure because of the greater mobility of NMOS devices, but at the cost of lowering pole at the folding point. To understand why, note that the pole at node X is given by product of 1 by GM3 plus GMB3. The total capacitance is known. The magnitude of both these components is relatively high. Ampere suffers from low conductance and figure realization of a folded cascode op-amp. M5 contributes to substantial capacity wide enough to carry the drain currents of both M1 and M3. In fact, for comparable bias currents, M5 and M6 in figure may be several times than M5 and M6 in figure. Our size as far as the our voltage swing of folded cascode op-amp is only slightly higher than that of telescopic configuration. The advantage comes at the cost of higher power dissipation, low voltage gain, low pole frequencies, as explained in session, higher noise. Nonetheless, folded cascode op-amps are used quite widely, even more than telescopic topologies, because the inputs and outputs can be shortened together, and the choice of the input common mode level is easier in a telescopic op-amp. 3 voltages must be defined carefully: the input CM level and the gate bias voltages of the PMOS and NMOS cascode transistors, whereas in folded cascode configurations only the later two are critical. And now we carry out the design of a folded cascode op-amp to reinforce the foregoing concepts. An important property of folded cascode op-amps is the capability of handling input common mode levels close to one of the supply rails in figure. For example, the CM voltage at the gates of M1 and M2 can be equal to VDD because Vx equal to Vy equal to VDD minus 500 millivolts. By the same token, similar topology using PMOS input pair can accommodate input CM levels low as 0. Telescopic and folded cascode op-amps can be designed to provide a single-ended output shown in figure A, for example, where the PMOS cascode current mirror converts the differential current M3 and M4 to a single-ended output voltage. In this implementation, however, Vx equal to VD minus VGS5 minus VGS7 to voltage of V out 2 voltage of V out 2 VB minus mod VGS5 minus mod VGS7 plus VTH6 and wasting one PMOS threshold voltage in this swing. To resolve the issue, the PMOS load can be modified as in figure B. Figure cascade op-amps with single-ended output. So that M7 and M8 are biased at the edge of the triode region. Similar area supply folded cascade amplifiers as well. The circuit of figure A suffers from two disadvantages with respect to its differential counterpart in figure B. First, it provides only half of the input voltage swing. Second, it contains a mirror pole at node X, thus limiting the speed of feedback. Systems employing such an amplifier, it is therefore preferable to use differential topology, although it requires a feedback loop to define the output common mode level. As a note, we recognize to achieve higher gain, additional cascade devices can be inserted in branch, shown in figure A. Triple cascade providing a gain on figure triple cascade op-amp the order of GM are not 3 cube by 2, but further limiting the output swings with 6 overdrive voltages starting from VDD. In the circuit, it is difficult to operate the amplifier from a supply voltage of 3 volts or lower while obtaining reasonable output swings. Thank you.